Hello everyone, Integrals 2, day number 3. We're going to do a quick lesson here today on the area between curves. So I'm going to sketch out a scenario here where I've got f of x, some form of a cubic function, or otherwise. And then I've got g of x, a linear function. And I've got points of intersection x1, x2, and x3. And I want to find the area between the curves. So that would represent this red space and this blue space. Okay, so implied within this process is, here comes my type A personality, even though these aren't straight lines. Don't be judgmental. I got my x-axis, y-axis. Area between curves implies positive areas everywhere. So if I wanted to find the area between, or the red space, I could do the integral from x1 to x2 of the upper function f of x minus the lower function g of x. All right, and then of course the blue space, if I took f of x minus g of x, I'd get a negative area. So we want to write that specifically as x2 to x3 of the upper function, in this case g of x, minus the lower function f of x. Now this can all be simplified by actually using the formula for the total distance traveled. So there you go. You can see, of course, I used ABC instead of x1, x2, x3, but we can simplify this provided we have the points of intersection of the two functions. I could go from A to C, or x1 to x3, of just f of x minus g of x and take the absolute value. So that's a nice little shortcut that you got available to you, but you got to have some skills on the calculator to find the points of intersection, as well as using Math 9. So let's get to it with a few examples, and then you'll have some time to work on a few of your own. Okay, so in example number 1, it says find the areas enclosed by f of x and g of x. You can see I've already graphed this, taken an image from my calculator. It looks like f of x is the blue graph, 2 cosine x. G of x is the red graph, x squared minus 1. If I want to find the area between them, I have to find those points of intersection. Now I'm allowing you to use the calculator here to find these. So to find x1, of course, you go to your graph, you press second calc and intersection, and you'll get that x1 equals negative 1.265. Now I would encourage you, you're going to want to go back to your home screen and press store or stow, and then press alpha A, stow that as A. Okay, and then based on the symmetry of this graph, x2 ends up equaling 1.265. So x2 you would stow as a separate value, stow alpha B, or what you could do is you could just make your limits from A to negative A. That's totally up to you. Okay, so now to find the total area, since this is just one area, one space, I'm not worried about writing multiple integrals. I'd just write one integral. A couple of different ways you could do that. You could go from A to B of f of x minus g of x. And of course, you've got those in as y1 and y2. That'll give you your answer. Another way you could write this is you could go, like I said, from A to negative A of f of x minus g of x. Okay, and it looks like, based on the calculations here, that the area comes out to be 3 sig figs 4.99. Okay, example 2, the area enclosed by f and g. So it looks like, at least based on n behavior, that f of x is blue here, and g of x is just a vertical reflection of f of x. So this brings about a bunch of interesting ideas. But let's first of all go ahead and just write out an integral such that we could find that area. Okay, so let's write out a general integral. Let's call this x1. We'll find those values in a minute. Then x2, and then x3. You might already be thinking about shortcuts that you could utilize to find this area or areas. Okay, and then this little area in the middle there. Okay, so don't negate or don't neglect the area right in here. Okay, so I would go from x1 to x2, x1 to x2 of f of x minus g of x, and then add from x2 to x3 of g of x minus f of x, g of x minus f of x. Okay, now another way that you could visualize this would be, of course, using the absolute value, would be from x1 to x3 of the absolute value, and you could go with either g of x minus f of x or f of x minus g of x. It does not matter. So f of x minus g of x dx. Okay, that would get you the same answer. Now a third way you could do this is I could, because these two functions are a vertical reflection of each other, I could just take double the area from x1 to x3 of the absolute value of f of x. All right, I could just take double the area from x1 to x3. So what would that look like, right? So let's find the area, well, not actual, but here's a green representation and the lower half of that portion. Right, if I doubled that, if I took the absolute value to find all positive areas and then doubled it, that would duplicate that green space to then also include the red space, which would be the entire black area there. Okay, so I had to find x1, x2, and x3. X1 I stored as negative 1.618. X2 ended up equaling 0.618. And of course I stored these, so I didn't put in rounded values. X3 equaled 1. So our area, when I evaluate with those specific values, I get 5.64. Okay, let's look at another interesting example in the next slide. Okay, I didn't give you a sketch of the graph here or an image from my calculator, so we're going to try to sketch this. I'm going to graph f of x, g of x, the x-axis, and x equals 3. So the area that I'm looking for is bounded by those four things. Okay, let's look at those. All right, so I got the x-axis. Okay, I've got x equals 3. I'm going to kind of put a vertical line here. I've got the function f of x equals 1 over x, f of x, and I've got the function x to the 2/3 power, which looks like this. Okay, so in between each of those, right, if I were to put a boundary around them, I'm looking for this Charlie Brown shoe looking space. All right, let's shade it in, kind of. All right, I'm looking for that area. Well, that area requires me to find the 3 points of intersection of the functions. There's 4 points, but I'm looking for the x values along here. So this is x equals 0. If I use my calculator, it looks like, and I guess I didn't really need it, this would be x equals 1, and now I've got my values, right? I can find the area, And the area here, I'm actually going to do the first area in blue. Okay, that first area in blue is from 0 to 1. And the two functions that I'm going to use are x to the 2/3, which is g of x, minus the x-axis, which is y equals 0. So I don't really need a function there, but I would do that, and then I would add that to the area, which I'll put here in yellow, from 1 to 3, now of f of x, which is 1 over x minus 0. Okay, so the area, if we were to do this with the calculator, would end up being, I believe, 1.70. At times you might be asked to do these problems without a calculator. Of course, the points of intersection will be reasonable, as well as the calculation for finding the integrals and evaluating those integrals. So just want to get used to the visual of areas bounded by curves, because we are going to move on into the next lesson in the next video on volumes of revolution, which require you to be able to find these areas. Okay, we got one more example. Let's do that, and then we'll call it good for today's video. All right, here we have example number 4. Find the area bounded by the following: f of x, g of x, h of x. Now, these values, of course, we got to find their points of intersection, so let's sketch them. I'll do f of x in green. All right, this would be the point 0, 1. And the graph would look kind of like this. It would go through the point 1 and 2. Okay, this would be the point 1, 2 as noted. Okay, the graph of g of x would be 4 to the x, which would go through the point 0, 1. And then it would go through the point 1, 4. Okay. And then 1 over x, h of x, that is, would be something kind of like this. It's not perfect, but this would be the point 1, 1. And the area we're looking for is going to be inside the 3 functions. So let's sketch it real quick. Just a quick sketch kind of to the side. We'll zoom in on that spot. It's going to look kind of like this. Okay, so what we've got here is we got a point of intersection at x equals 0. We got a point of intersection here at we don't know. Okay, we don't know what x equals there, but we can find it. And then as well as here. So this would be, we could call this x3, x2, and x1. Okay, so using the calculator, x2, this point will be where the where the red and the blue graphs meet. So that's where 4 to the x is equal to 1 over x. That's not necessarily very reasonable to do without a calculator, so a calculator would be required on this question. And x3 would be where 2 to the x equals 1 over x. Okay, so I found using my calculator that, of course, x1 was 0, x2 ended up being 0.5, and x3 ended up being a value that I stored but rounded would be 0.641. Okay, so the area would be the integral let's go from x1 to x2 of the red graph minus the green graph. So that would be g of x minus f of x. Okay, so that would accumulate area from x1 to x2, and then we would add the area from x2 to x3 of the blue as the upper and the green as the lower. So that'd be h of x minus f of x. Okay, so calculation, math 9, all that good stuff. I see an area that comes out to be 0.163. Okay, guys, the one last thing I'd tell you is that as you're doing these problems and you get an area, it can sometimes be deceiving, and you just get a number and you think, okay, I'm done. Okay, just look at the context of the problem. And of course it matters, right? If I zoomed in on this, I wouldn't necessarily have a good perspective on how large this actually is. But if you look, I mean, this is, you know, I could kind of estimate that this is going to be, you know, it's definitely less than 2, right? Because this rectangle that encloses it would be an area of 2. It's going to be less than 1. I can tell that for sure, because it would be enclosed in a square 1 by 1. So 0.163 seems reasonable. So make sure and check just the whether or not your answer would fit the context of the problem. All right, that's it for integrals 2, day number 3 on areas bounded by curves. See you in the next video.